So,
I know. It's like absurd. I have to use a mouse to do something.
the thing is, all right, before everybody else gets nuts,
Get a closer look at the hardware. Huh?
Yeah, we'll do that.
problem being farsighted. Yes, I can see to the future, but it's really hard to read it. Ooh, it's like Ben Eater style.
It is the name one, actually.
Oh, okay. So what, I guess you're gonna tell us about the difference with the 6505. I know the
Hey, there's
6509
Chris.
is what was in the Commodore 64.
There's
so
Mike.
it didn't get used that differently. So.
All right, well, I'll just go around. I think maybe some people can see it close.
Oh, okay.
All right, so tonight's the show and tell. Hi. Oh, I guess I should say. Right.
Yeah,
Hi,
no,
Mike.
Hi, Mike.
Hi, everyone.
Hey, Mike.
Thanks for having
Nice to
me.
meet you.
We gave this talk last week down in Canton, and I guess you guys didn't care anything about the 6502 because none of you were there. Well, three of you were here. And so they said, well, why don't you come up to Akron and show off the board, and people might be interested in that. So,
Oh, yeah.
So this, I don't know if you'd be interested in this at all, but this is just a hobby board. So this is just a hobby thing.
Mhm.
And anyway, so this is a Ben Eater style board, if you know what that is. And what happened was at the end of the year, I always have vacation I got to use and lose. And there was a COVID thing. I don't know if you heard about that. So we were all locked down. So I was like holed up in my house last December. And when I was younger, I did a lot of breadboarding and I built stuff. And now I don't do that anymore. So I just, after watching Ben's videos, I got excited about it, started doing it again. So I built this board. And mostly to do some breadboarding and to learn 6502 assembly, because I've never done that before.
Oh,
And
wow.
I was curious about that. So I built this last December, got to Hello World, and that's about all I've done with it ever since. And I got some ideas what I'm going to do with it afterwards. So, but since it's a Linux group, or at least Canton's was a Linux group as well. So I do have a Linux computer here. So this is my ThinkPad. It's a Linux machine, and we're going to be using this to program this guy tonight.
Cool.
So that's what we're going to do. So what I'm going to do is do a really quick overview of the hardware, and then we're going to step through. We're going to create a blank ROM image, okay, and then we'll just go with no ops and put it in here and watch it just implement the program counter. And if we can get that far, that means we can actually make the program. And then we'll step through some simple things, and hopefully by the end of the demo, we've got 4 toggle switches here connected to a port, and so we can input one binary hexadecimal byte, one nibble. And if we can get it that far, I stole this 7-segment LED display. I stuck it onto the other port. I stole off the old kit, and I put it on the other port, and we'll try to display it on this guy. That's the goal. So this is the device. I'll pass it around so you can take a closer look. The zero's kind of far away, and I got some pictures too. The breadboard itself, I actually had that already. It was just a breadboard I had bought some time ago, and it had it has this base on it. It's already built in. The bad part about that is that you can't expand it anymore, so it kind of constrains you. But
Now, is that a 6502 on it? or-
yes, there's a 6502 on it. So yeah, let's walk through the hardware real quick here. I've got
So,
yeah, so that's a 6502 device. Let me just jump to what's on the board itself. So
I don't know if you can see that on on the screen. There you go.
can you guys see that okay?
yeah.
Okay, so the
Oh,
board
where's
itself,
that in the way?
so this is a 6502 processor. It's actually a modern 65CO2 processor. So they still make these guys today. And they still sell a lot of them. But so this is a modern version of the 6502. And some of the, I guess, some of the enhancements from the older versions that one of the nice things about this one is that you can actually stop the clock and it doesn't lose its brain.
Oh, yeah,
So like the
CMOS.
old ones, you have to keep the clock going the whole time. Yeah.
I'm sorry to interrupt you. I
Go ahead.
got this question I'm thinking of. It's going to go away. With
Yeah.
Assembly that works on a 6502, would that work on a 6520 at the same time? Or do
I
you have to
don't-
make changes?
I think that's different. Yeah.
Okay. It
Yeah.
makes sense.
Yeah, there's different 65s. So yeah, this is the 02. So that's the one that Ben. So the back up a second. So this design comes from Ben Eater, who got that from a guy named Garth Wilson, and there's a 6502.org website that's got tons and tons of information. about the for hobbyists. And
his videos are amazing.
yeah, and Ben's videos are freaking amazing. So actually, he had another video that I was more interested in was where he built an entire processor out of TTL logic.
Yeah.
Right?
Oh, I saw that.
And that's like a beast, right?
Yeah.
So I wanted to do that, but I only had like so much vacation to use, so
So much money.
and so much more time, I think. And so I decided because and I justified it in my mind because I wanted to learn the assembly code for 6502. When I was younger, like in the 80s, I did breadboarding in college, but we used like 8080.
Mhm.
And
Right,
80,
that's what I,
8086, I think. So, but I never. So then I started with the Z80, and then the 8080
Mhm.
and 8086. So those are the ones that I used, and then I kind of skipped over a 6500 series, and I also missed the 68,000 series too. But anyway, so I thought I'd go back and for nostalgia's sake do this processor. So we have that processor. We've got a 32-cut 32K RAM, 32K EEPROM. It's actually an EEPROM. And I added Ben. He puts it in and out of the breadboard over and over again. I can't do that. I broke the pins right away. So I bought the zip socket, a zero import
Nice.
socket,
Yeah.
so you can put in, but you do have to put it in the correct way, right, Casey? That's what I did last week. I turned it around the wrong way, and I was
Well,
like,
poof.
"You guys smell something?"
Just Dante, be careful. You smell like he's trying to burn the building down.
Mhm.
Delicious.
It happens. So and then we got it. And then there's one quad NAND gate that's used for the address decoding, which I think is really cool. So that's part of Ben's design, and he walks through the whole thing. I mean, when Ben, if you're really interested in doing this, it's really easy to do if you follow along his videos. He starts with just putting the processor in the board and just put the power lines on, and just one step at a time. He walks the whole thing. First the processor, and then the ROM, and then the ports, and then the RAM, and he goes through the whole thing. So it's really fascinating videos. We have a 1 megahertz clock on this guy, but we also have a clock module, which is that's used for testing. So we can single step the clock we want.
Oh,
And so we can watch if I to do that. And then we have an LCD display, 2x616, I think, LCD display. But tonight we're not going to use that. That's way too complicated. We're just going to use the LED tonight. And we've got the power supply, and we've got to make the ROM. You have to buy a burner. This is another like $80-90 for the burner, and the software. There's Windows software, but you can also get download. There's an open source software for using this guy, and it's on GitHub, and it's a command line tool that we'll be using tonight to use this thing.
so you can't just build one of those off an ISP 500 or something?
You could build one of these. I just bought it though.
Okay.
I think I got my phone.
And also, this guy has a this Arduino sitting off to the side here. This is just my Ben shows how to use this Arduino for as a poor man's line tracer. So this is what this is for. It's just a line tracer. So what I did is I took the lines, the data lines and the address lines. I just brought them down here to this last board, and this is plugged into the Arduino. So he's got there's a tiny little Arduino program just to sample the lines, the data lines and the address lines. And as the clock goes off, it triggers, and then we'll watch those on the monitor. So it's a very cheap, low budget hobbyist line tracer. So just a real quick, I'm kind of going to go over this kind of quickly because I want to do the programming, because I guess I'm a software guy, so that's what I want to do. So this is the clock module. So this clock module actually comes from Ben's TTL computer. This is the exact same clock module he uses on his TTL. He sells those things in modules. You can get like an ALU module. You can get the all the different modules. So this is just a clock module. So what this clock module has is it's 555 for the timing, and so you can variable timing for you can do like 0 up to 10 hertz, or you can switch it, hit that switch, and then you can do a single step mode.
Oh.
And this chip is just to debounce that switch,
Mhm.
and then this chip is just to debounce that slider. So you can actually change modes while it's running.
Oh.
Because if you don't have debouncing right, when you slide it over, it's gonna the clock gonna go. So you can change mode as you're running. I added another. This is the actual running chip. So
1
that's
megahertz.
the 1 megahertz clock. So we can do the test clock or the actual clock, the production clock. And I actually added, since I took this picture, another slider switch, but I can only use it when the power's off. So you can switch modes, but only when the power's off. Because I don't have any debouncing for that right now. And then this is something that I added extra, which was the auto reset on power up. So on Ben's computer, so like the 6502, when it starts up, all the registers are haywire, and you have to have an external reset signal on it over like 2 clock cycles or so. And so what Ben did was, in his videos, he just has a push button, you hold low, and then you run the clock for a few times and it resets. And after a while, I got really tired of that. So I looked up some clock or some reset circuits. And I got one off of the 6502.org, which is, I think this is the same one that's used in one of the Commodores.
Is that another 555?
Yes, and that's another 555 that's used to, basically, there's a large capacitor. No, that's just a power line capacitor.
Yeah,
This is a
sorry,
large
that one
capacitor here,
Mhm.
so it's just coming up. So when the power comes up, that capacitor charges up, and this 555 is used like as a comparator, so it's like a one-shot in this case.
Yeah.
And then the reset goes, and then there's a manual override, so I can reset it manually too. And then this is of course, the microprocessor. Off to the side here is another push button, which happens to be wired to the interrupt, so I can do an interrupt signal on that guy. And that's the Hello World ROM that's in there right now. So that's the ROM with seated in the socket. And there's the RAM, and that's yeah. So this is a read-write memory.
How much you got?
Well, there's a 32K RAM. So 6502 has 64 address lines, so it gives us 64K of address space. And there's the ROM is 32K. The RAM is 32K, but we're only using 16K of it, the top half. And the reason is all the address decoding is being done by this one chip down here, which is the address logic. And I got some, since the can't meet up, actually, I did some more documentation on that. This is the IO port. So this is a 6522 versatile interface adapter. So this has 2 IO ports, 8-bit IO ports on it. It also has interrupt handling and timers on it. So I'm not using the timers. And right now the ports are just wired up to the LCD, but then I brought them down to this last board for our demos tonight. So in terms of, yeah, so the memory map, like I said, we have 16 bits of address space to deal with. So the ROM's taking up the last, the bottom half, 32K. The RAM sits at the top half here, but we're only using the first half of the RAM. And then the IO ports are addressed in the middle here, starting at 6,000 hex. And then there's some free space here that we can use for in the future. So right now they're reserved for future use. And the reason it's kind of laid out this way is because the processor itself, the 6502 processor, which you guys probably all know, it's like it's an old device, right? It's like maybe 75 or so.
Yeah.
So when they did that, they had to cut a lot of corners, right, to get it to market, to make it really, really cheap. So there's some stuff that's like weird about it. Like a lot of stuff that's really weird about it. But it's quirky. And
That's why I never.
that's what we like.
It's
So-
a 16, it has 16 address, but only 8 bus. Much like the 86.
Yeah, so
88, sorry.
there's a couple things in the hardware that it expects to be in the address space. For example, the first 256 bytes are considered page 0 of the memory. So if you think of the address space as being 8 and 8, you have 16 bits. So the high half is the page number, and the low half would be within the page. So that would be page 0 is reserved for special fast fast memory allocation. So it acts like a whole set of 256 registers. So it's called page 0. So there's instructions that are specifically for page 0 that you take advantage of for optimization. And then the stack fits on page 1, and it's 1 page is stack. It's tiny. It's like minuscule. I can't believe anyone would come up with this design. It's insane. But
There's a great video about why they chose this. They didn't just have to grab it. They specifically talked to people who are like, we're gonna make this elaborate chip. They're like, it's not what we need. We'd rather have a cheap chip
yeah,
that just gets us going.
that's, yeah, exactly, yeah, so what you could do is you could have a functional machine, actually, with no RAM, you can have a functional machine if you don't want interrupts and you don't want, if you don't want subroutines. You can just use ROM, but you have to have at least a stack, so you can if you make it this small, you can just have only a few bytes of RAM, and you can have enough stack that you can service interrupts. And so, oh, and at the end here is something called the vector. So there are 3 vectors down here, and one of them, the most important one, is probably for our purposes, is going to be the reset vector. So when the thing first starts up, it jumps down to FFFC, and it sees what's in that address, and then it loads that into the program counter, and then starts counting from there. So your program can be starting somewhere within ROM, or somewhere in the address space. That part you can change. And then the processor's registers are minuscule. Like for me, coming from like a Z80, I'm like, oh my God, where are the registers? There aren't any.
You think it's a deadly chip, you know? You forget.
It's a great chip.
Yeah, a lot of stuff in there. Like I guess I was spoiled. But like so you only have an 8-bit register accumulator for general purpose. You only have one 8-bit register, general purpose register. And then you have 2 index registers, X and Y. And these and the A register doesn't even have an increment. You can't even have an increment on the A register. You can only increment your index registers. And these are for indexing it to memory, basically. And then the program counter registers, which you can't really mess with. They're just, that's where the next instruction is. And these are set by branch and jump instructions. And then the stack pointer, and then they show 1 here to show that's always 1. And that's for push and pull, push and pop on for the stack for subroutines. And then you have a set of flags. They're called program status registers that get set based on operation. So this is how you do your branching. So for example, if the A register is 0, and the instruction sets that to 0, then the Z flag gets set to 0. And then you can have a branch if that flag is set.
It has a BCD mode.
Yeah.
Yeah, yes, BCD mode, and you can disable, interrupt, and then there's some, the overflow flag and the negative flag. Negative flag.
I'm just thinking like for talking to
But I went through that really fast because I figure you guys already know all this stuff, and it's just a refresher, right? And also because we want to do some demos.
you can't remember.
Oh, okay. One thing I did since
A lot of people used the 6502, that was original Commodore 64.
Right.
Yeah, it was an Apple
20s.
and Atari 2600s.
Yeah.
And,
Apple use that or
Yeah,
6800?
No, they were going to use 68.
Oh, that's right.
That's right, because they were going to use a 6800, and then kind of like the 2 was a lot cheaper. Yeah.
okay, so this is my GitHub for this. It's just Mephi 6502. So if you want to send some pull requests, I'll review them and work quick. So we have this is the demos we're going to go through today, and since last week I added this memory map because I was thinking about this a little bit more. So I added this page which shows a little more details about the memory map we're using. And oh, you probably can't see that too good from here, huh?
Manually assembled.
There you go.
So that's
Wait, you don't have a big file to zoom in on web pages? I'm disappointed, Mike.
I'm sorry to disappoint you. Make Zoom.
Make Zoom.
So we have the memory map. So what's interesting here is that so bit 16, bit 15, which is high order bit, when that is 1, we're using ROM. If it's not 1, then we're using either RAM or IO. And then we look in the next bit in. So if this bit is set, then we're using IO. And if this bit, if this bit is 0, I should say, we're using RAM. If it's not 0, we're using either we're using IO, and if this bit is set, then we're using the actual IO that we have today. And this is not my design. This is just what Ben does in his videos, and it's based on Garth Wilson's address decoding page. Which actually goes into great detail about how to create different types of decoding logic. And the one that we're using is I did a slimmed down version. I went through all the actual decoding states because I just wanted to verify this was what I thought it was, how it was designed. So I made a truth table, and this is actually the actual circuit that we're using today for the decoding of the different components. So if A15 is low, then we use the ROM, et cetera, et cetera. And the only thing that sticks out here is this clock is actually controlling the RAM, because there's actually the thing these are every chip has a chip select, right? So ROM has chip select, the RAM has chip select, has 2 different chip selects, and then the ports have 2 different chip selects. So we're using those to say which thing is actually being used at any given time. Otherwise, there'll be collisions, right? All right. So with the preliminaries out of the way, I want to do this. I want source. There's the make file. I knew there'd be one in here. Okay, so first of all, we want to be able to make an image, right? So, excuse me. So the way Ben does that is he actually writes a Python program, and that's how he starts off. He makes a Python program that creates the image file, and then he kind of tweaks that for a while. And the idea is that we want to start with machine language, because we're starting at the bottom, right? So we're going to start with machine code and work our way up to assembly. And I figured since this is a Linux group, we probably don't want to use Python. We're going to use Linux commands. So let's use DD to make a. So if I
Oh my God.
right, yeah, exactly. So if we're gonna cat dev 0 to make a bunch of zeros, right? And then we can pipe that into DD and say. So we can make a ROM bin file. Can you guys read that? It's probably too small, huh?
Yeah, what is it?
How's that?
Yeah, that's easy.
Is that good enough?
Yeah.
That's
Thank you.
actually better for me too. So we'll say we're gonna make a ROM bin file, and say the block size of that will be 1K, and it's a 32K. It's a 32K chip, so we'll do 32 count. So if I did that right, that'll create a. So yeah, so there we go. So then we got a blank. Me too. So this makes me happy. So now I've got a binary blob, and I can put it on this guy. But before I do that, actually, I don't want zeros in here. Actually, I want to fill this with no ops. So that's E8. I'm going to use, I will use translate to translate those to EAs. Yeah, TR. So I should go to my documents. I've got a couple of old documents here. Oh no, ops is way too complicated. We're not going to do that.
You didn't expect to feel it.
No. Okay, this is what I wanted. So this is the data sheet for from Western Digital data sheet. And here's the opcode matrix. Oh, we're blocking the screen. a little
Oh,
bit.
that's me here.
No,
No, it's the computer.
So if you look at this opcode table, this is hex, right? So actually, if I go here, EA opcode is no op is EA. And actually, there's another chart that's
Makes sense because electronic arts are really hard.
I don't know. They're bit patterns. I guess there's a reason they get stuff like that. But if I look down here, this chart makes more sense, right? Here's the instructions, and if I come down here, I can see. Here's no op. No operation is echo A.
Yeah.
So we want to fill that. We want to fill that guy with EA. So we have. So let's. Oh, one more thing. TR doesn't like to take hex input, so it likes octal. Yeah, unless you're using bash, I found that it wants octal. So EA. So EA is 352 octal. 352.
Yeah.
Is that right? Do my math. Check my math. 352. Did I get that right? So we use DD to make those EAs. There we go. So it's full of EAs now. So this guy's full of EA. So I want to put that on the chip itself. I have to run.
Oh, Minicom.
So Minicom is the program. Oh, no, I'm sorry, Mini Pro, not Minicom.
Talk to it like it's a.
Yeah,
Yeah.
yeah, Mini Pro. So this device is called a Mini Pro. The programmer, the burner is called Mini Pro, and the guy that wrote the software to interface with this, he just called the command line Mini Pro. And so you can look it up on GitHub. There's a GitLab, I think, the Mini Pro open source project. And we got to tell what chip it's on there. So it's a AT.
We have to hurry then, because they're about to start deleting things that haven't touched it. No, this is the new thing after getting that.
Oh, is it?
Cheapskate. Really cheapskate.
So we're cleaning stuff off.
Oh, yeah, they want to say.
Stuff that's been.
Yeah, it's just like when
stuff that's just
the
been
BBC
idle.
was getting some space back by deleting all those old films. And it was like,
Yeah, well,
which you could
who
never.
needs archives?
All right, so it actually seems to work. Put something on there. So now we'll pop this in here, and this is the part where I got to put it in the right way. Right, Casey, double check this.
Hey, Mike,
Yeah.
do you remember that time
Oh man, I remember
you did? That's incredible.
I put the chip in backwards, and the whole place burned to the ground.
Yeah, it killed those two people.
I didn't realize Stark County had it so bad.
Yeah.
Yeah.
We're exaggerating just like only slightly. All right, so I got to plug in the Arduino now, so you can see when we put this up what it's going to do. Let's see. Look, Phil, I'm going to use a mouse to start it. Is that okay with you?
It's fine. You do what you want. I'm just.
Don't mouse shame me, man.
I'll change your files for all the things.
Got a mouse
My
shame.
bad.
Look how fancy this
Sorry
GUI
for
is.
having faith in you, Mike.
All right. So first thing I do is I check to see if this thing is actually communicating. So I'll download the thing. So here's the program. All this program does is, and this is from Ben's video as well. So all the program does is that maps the I/O pins on the Arduino to what the address pins are that I plugged into. So these are the addresses are plugged into Arduino. So I would say that the processor address A15 to A0 are plugged into Arduino's 22 to 52, and the data lines from the processor D7 to D0, those 8 data lines are plugged into the Arduino 39 to 53 numbers here. So then there's a little Arduino program here that just checks it just sets those to input mode. And then basically when the clock, there's another one that's, we have reset, clock, and read write bar. So the read write bar is the pin that from the processor says, for the addresses I put on the line, am I expecting to read from these or write these? And then the clock is the clock cycle, and then the reset is the reset, the power up reset. And so when the clock pin goes off, the Arduino grabs the values of these things, and then we do some bit shifting to get a number, and then we print F the number. So we're going to print basically every time the clock goes off, what the address lines are set to and what the data lines are set to. And the way we see that is we just run the Arduino serial monitor. And the first thing is that we had to make, this is kind of small, but we got to make sure the baud is set right. So that's set right. So now I got to plug this thing in and see if it smokes. This is our smoke test. And I just,
There you go.
oh yeah, oh, it's going. Yeah, so yeah, it just jumped to EA, so we went too fast. Sorry, let's start over. Reset. So let me hit the reset here. And we'll single step it. There we go. So now it's going through the reset sequence. Can you guys see that? Is that too small? I can try to make it bigger. But right now it's going through a reset sequence. So now it actually hit this. I don't know if you can see it, but it says here FFFC.
And that's the bottom stuff. Yeah.
Yeah, the bottom of the screen. And this is, remember I said that's the reset vector. And it's reading it and it's getting EA, which is what we put on that chip.
Mhm.
So now it's reading so that's the low end of the memory. Now it's reading the top byte. So what do we expect the next thing to happen? So, yeah, you're right, yeah. And we've jumped to EA, which fortunately our ROM is low enough that that's in our ROM space. And we read and it's EA. And so now we effectively we're successfully doing nothing. So this is our hello world, right?
Yeah.
And this is great. So now it's incrementing it's EA, so the EA goes off, and then this is just a count. And what it's doing is just basically running a no op for one operation, and then it reads the next EA, and it's incrementing
The address.
the address until it gets down to the end where all hell breaks loose, right? It's going to eventually wrap around. So I'm not going to press the button that many times. I think I can make this font a little bit bigger here. Let me do that real quick.
Oh, you have to restart, I think. 'Cause it's okay.
Yeah, I think so. That's okay. We're powering down anyway. There's a preference font.
Hey, Mike, does
Yeah.
the control plus minus not work when you're?
Not in Arduino IDE.
Oh, it doesn't?
Because it's really old school. They've now got Arduino 2, but that's missing a lot of boards, as I just learned. Like,
Oh.
Oh yeah,
you wanna
that looks better.
you want to control an ST M32? No.
Yeah, is that bigger?
Yeah.
Yeah, that works. Okay.
Let's see if I can get it to focus.
So now that we can do nothing, what's the next thing I want to do? Oh, I want to do something. So I'm going to write a program. Let's write a program now to put a byte into the accumulator and then write it off the RAM. That sounds exciting.
I know, I'm good.
And then we can do nothing and then jump back to the nothing. So we'll just be in a loop, right? We'll just spin like that. So this will be our first program, and it'll be machine code stuff. So in order to load something, and I picked this this guy's, see if I can make it a little bit bigger here. The accumulator, yeah. So let's put something into the accumulator. And LDA, so this is like the most popular, this wins the popularity contest for instructions on this guy, like most instructions you know. So we're gonna load in there, and then you see this other column here. So this is the first thing I learned about the 6502. It doesn't do much, but it has all these different ways to address addressing modes, right? There's 16 different addressing modes.
Yeah,
Yes,
it's insane.
it's 16 different addressing modes. So you can say, and I don't have them all here because So here are all the different addressing modes. So if I do an LDA, I'm going to say, I'm going to load a number, and I'll say the next number in the ROM is the one I'm going to load. That's called immediate, load immediate. So if I do an A9, I know that that pound actually means load immediate. So if we say A9 and then a byte, it'll load that byte into memory. And then these other things are just different ways of loading. So you can load from an address. You can say the next bytes are the address to load from, et cetera, et cetera. And then the ZP over zero page. And you can see not every instruction has every addressing mode. Some of them just have one. But so that's, to me, that was one of the more complicated things to learn about this guy. And I'm always confusing myself about it still.
That is the most confusing thing when you have to hand assemble that stuff.
Yeah.
And to think von Neumann building people for having symbols.
Oh, yeah. We're going to get to that. You can yell at me for that. So,
Oh, I will.
oh, thank you.
You're welcome.
You guys got to come more.
So, so we'll say A9, and we'll load in. Oh, wait a second. Let's do it this way. Oh, how do you get a VI? Does anyone know how to get a VI? Okay.
Reset button.
Here, we'll use my lighter.
What I'm gonna do is I'm just gonna dump this guy to before I was dumping it to screen. Now I'll dump it to a file, and we can edit this guy right here. So yeah, we're gonna do this old school A9. I'm gonna put the number 8 there. So now this first instruction will be, but also we're not gonna go there though, right? We're gonna go to EAEA. So we gotta actually go down here to the bottom and put in
Right.
0080. So it's little endian. So we gotta put the low byte in first and then the high byte. Now it says 80, it's gonna go to 8000, which is the first byte of the ROM, which is 0 here because we're offset by 8000, right? That's a little confusing, but if I say 8000 in the address space is 0 of the ROM because we're down, right? So the first thing we're gonna do is gonna load 8 into the accumulator, and then we're gonna write it out to memory. So that's gonna be an instruction. So that's to be a store instruction. So that'll be store A. Now I gotta make that a little bigger for you guys. Yeah, store A, and we want to store it at an address. So that'd be 8 dog. So that's just an address. So we'll store 8D. Oh, I got too many windows open. And I'm gonna store it at 0020. Oh, that's right. 00, no, 0002. 0002. So that'll be page 2, the first address there. Right, and then EAs do nothing. And now, so then we store it, then we're not gonna do nothing, and then then I'm gonna jump back, I'm gonna spin. Actually, that's good enough for now, I guess. Well, I guess I don't, I know I wanna show an address. I guess we're kind of pressed for time, so I'll just skip the jump. I was going to put a jump here. Well, the jump is actually you just have to trust me. It's 4C.
Breadcrumbs.
Ah! Thanks, BI. You're not being helpful, BI. 4C, and then we want to jump back up to the EA. So this is going to be 8000. 1, 2, 3, 4, 5. So that's 8005. That's 05. 80. And this is our first program. Oh, so we got to make that go back to the ROM, right? So we got to, so that's the ASCII. So we got to put it back into the binary mode. So I'm going to do a revert. So XXD is an awesome program. You can go the other way too. So you can dump binary a file into a binary file out into a dump file, but you can take a dump file and go back into a binary file. And that's with the R command. So the first option is the file we're reading from. And the second one is what we're going back to. So we're going to clobber this guy. And it's there. All right. And we got our thing at the bottom. And, oh, I got to put the chip in and put it in the right way. And we have yeah. So as you can see, machine code programming is not very practical. It's fun once.
We had back in the old days.
Be glad you're not putting that in with dip switches.
Oh, yeah,
my
well,
God.
But
You know, I didn't do dip
We did
switches. I
that.
have Thomas here about.
PDP-8. Mhm.
So we got that in there now, and we're gonna fire up the Arduino. Clear this guy out. Yeah, there's a lot of reminiscing going on here.
You had ones.
Well,
Clear this guy out. All right, okay. Get this set on single step mode, yeah. Okay, so now it's doing its reset cycle. It takes about 7, I think. So it's reading, so, okay. So it read, before, remember it read EA, now it read 0, 8, 0. So that's our interrupt, that's our reset vector. So now we expect to jump to our program. And the first byte was A9, which is load the accumulator. And what we're going to load it with, the next byte is 8. So we're taking 8, we're putting it into the memory, into the accumulator. And now, oh, 8D, that was store. So it's going to store 0200. So this is 0200. So it should write to RAM now. And there it goes. There's our W, right. So now we're writing to memory address 0200, which is right after the stack. And we're writing the number 8. And now we do EA, which is nothing. And you can see this is the address, so it's going up.
here's that 4C.
And there's 4C, which is the jump. Well, I didn't show you in the manual because I'm trying to go a little quicker, but yeah, that's 4C is jump. And the next thing it should be reading is the where to jump to. So it's 8005, which is, we've seen 8005 before. So what's 8005? No op. So it should go back to there. So now we're in a loop. Now we're just running in the loop. So that's our first program. Yay!
Boy.
Okay, so like you said, so people like on the ENIAC, right? They're like, this is how they program it, right? With opcodes. I'm like, wow, that's all fast. But then they said, well, there's got to be a better way. As soon as they did that, management got mad. It's like, why are you wasting computer time writing programs to do this? We have people that can translate this stuff for you, right?
It's right back to the, when the first phones were introduced and the British started hearing about them. They say, well, maybe the Americans need that, but we have plenty of messenger.
Right. So the idea is, what if we just took that, right? What if we just said, well, instead of writing like the binary, what if we just had a file that listed the commands? Like, what if I just had LDA 08 and STA 2000 or 0200, and then I just have a program just translate that into the hex for me.
Mhm.
And that's the idea of an assembler,
Mhm.
right?
Yeah.
So I was thinking about that. Well, how hard would it be to write an assembler? Right? It shouldn't be too hard.
No, this is a translator.
So, also with the assembly, we got the no op, and then we got the the loop here shows the address. So the assembler can also take care of like handling the arithmetic of where addresses we want to
Yeah.
visit. Because we had to count right to go back to 8005. But the assembler can keep track of that. So he knows that, well, that took 2, this took 3, so I'm at 5. So I know if I'm going to jump to this loop, it can be set to 5. I can remember that. So I can do a 1 pass, remember all the addresses, all the labels, and the second pass fill them in. Right, because it might be jumping ahead. So I thought, well, let's do this, right? What if we just had what if I just wrote a bash script to convert this? So So first thing I did is, well, if I had a bash script, what I could do, like just to proof it, proof of concept, I could just strip out the comments with said, and then I can just see if I got the opcodes out, get the opcodes out. So that can grab just that stuff out. And then once I have the opcodes, I can do just a lookup, just a quick bash script in a couple of minutes, so I can have something almost working. And then I can just do a case statement and grab the stuff out and then print out the hex. So that goes from, really quick and dirty, text file to just a list of codes like that. And then with that, I can just I can do plain mode in XXD. Say my input is coming from standard in, and I go ROM bin, and that'll actually write that to the ROM, and attaches the ROM with that hex. So I'm like, pretty close, just in a couple seconds here of having assembly. So no, I'm not going to do a lot more with that because people have written assemblers, but it's just good. The reason I'm doing this is to learn about stuff, and it's kind of like get your hands on it.
Build a next one.
So yeah, so right now I just have POC proof of concept, but what if that POC code was actually an assembler? Then I could self-host.
Neat stuff.
So I can bootstrap it all the way up. But what Ben uses is an assembler called VASM. No, it's VASM.
Instead of MASM, we used to use MASM.
Yeah, there's MASM still around. There's different assemblers you can use it for 6502. This is a simple one. So this one is a portable
Amiga.
assembler that targets a lot of all these old chips, and it supports a bunch of different things.
Rachel, like that one, has an Amiga.
Oh yeah, it's got all the different. It supports all these different processors. We're gonna do this one, which is actually.
It does V4. I have a machine.
Oh, yeah.
Yeah.
Cold fire.
And the way you do this, you just download the code and then you specify. You just use the right makefile for platform you're on, and then you specify the syntax. So I downloaded it, I built it. I said the CPU I used was 6502, and the syntax we use for this is what's called the old style syntax. This one right here. There's different syntaxes. So that's the thing about if you're learning assembly, there's different syntaxes, even for like the same architecture. There's different assembly flavors, right?
Add Mac. That's interesting.
So I already downloaded VASM and built it like that. And for this. So this program is the old style format, and this is basically what we did by hand, right? So it's load A and then store into 200.
Yeah.
Load 8 into the A register and then store that in RAM. And a couple of things. So the dot things are called directives. So this is a VASM directive to say that the offsets are, the ROM starts at 8,000, right? Because we're gonna have a loop here, and it's not gonna be 5, it's gonna be 8,005. And then down here at the bottom, we have another offset to go to all the way down to FFFC, which is the reset vector. And we're gonna plug in, instead of putting 8,000 here, we're gonna actually put in start, which is the label. So it's gonna know, it's gonna fill that in for us. So it's gonna do some things. And then there's one word at the end here that we're not using yet. It's another vector, but we have to have that so we fill out exactly the 32K. And Phil, pay attention. I'm gonna run a make file.
All right, that's what I'm here for.
So if I run this make, it actually builds all of them. But if I do make, you take the. You should do a talk on make. It's a really useful utility.
Casey's on deck for that. The Three Musketeers.
Oh, okay. Oh, I added a target here. So I got target typing these commands in over and over again. So I made a make file. And so this target it'll run. Well, we ran VASM already. So it runs VASM and creates the bin file, and then it runs the mini pro command to put it onto the actual thing.
So when it's writing, that's the actual writing.
Yeah, it's writing to the chip.
I was wondering why that.
So it does a write code to this guy, and then it reads it back and verifies that it read what it wrote. And sometimes it's not, and it fails verification. And it's usually because I didn't put the chip in right, or it's loose, or got to reseat it, or I burned it up doing something I shouldn't have been doing.
You wouldn't do that, would you?
Well, I did break some of the pins off one of these chips, and then I soldered the leg on, and then like it would only burn on the thing like 1 in 10 times. That was really frustrating. So I bought a bunch of ROMs that were spares. All right. So if we do this, this shouldn't be exciting because this is just the same program actually. Oh, here it is, yeah. So it's the same thing. It's in sleep already, so we'll turn that off. So what's the next thing I want to do?
Lights.
Mario. My daughter's like, well, can you Google with that thing?
Look, it's a C64 processor. You start with junk man.
Yeah,
Then
you work your way up.
You get Doom running.
Oh yeah, we want to light. We want to light something up. We want to light with this LEDs, right? Zoom? Did you say Zoom?
Doom.
Oh, Doom.
Doom.
Doom. Well, that's better. Yeah. Oh, so yeah. So I call these. These are called .s for source. So demo. That was demo 0. So demo 1. So demo 1 is going to be a little more exciting because we're going to actually write to the output port. So what we got to do is yeah, we got to set up the port. So there's 6,000 is the start of the I/O ports. There's 16 ports. Yeah, so the first 2 is like A and B or the data, and then, but then like 6,002 is the data direction control register. So we got to write to that data direction control register to say which pins are output pins and which pins are input pins. So right now, we're going to make them all output pins. Demo 1.
Memories from about 40 years ago.
So set them all to output. And this says, oh, this turns on just pin. Oh, a couple of things I glossed over. This hash here means that this is an intermediate instruction. This is something I get wrong all the time. So if you don't put a hash here, or you call octothorpe, a pound sign. What do you guys call that? Literal. Yeah, that's a literal. So that's a literal value. If you don't put that there, it's going to actually use the address of that number. So it's a different addressing mode. That's what tells it. So actually, this LDA will go to a different will be translated to a different opcode because it's a different addressing mode. So that means that's a and then this dollar or dollar signs are just means that it's hexadecimal. If it's doesn't have a dollar sign, then it's decimal. Dollar sign is hexadecimal, and the percent sign is binary. And I don't think there's one for octal. At least on this, this guy. But so let's see what I do with the chip. So let's burn this guy. So this should turn on. So I've got this guy connected to the output pins on B. So we should light one of those segments if this works. If it doesn't work, I don't care.
Giving up on life, are you?
Yeah, it's too hard. Burn. So I gotta say with the image I want to burn.
Should have brought my
Which number am I on? 2?
MMD1, which is a 8080 trainer.
Oh, neat.
It's a computer.
That's what to say. You need to do it 3 times.
It was a offset. Offset, which if you had a 16 bit and 8 bits, octal doesn't line up.
No,
It's 460.
it's 3.
Yeah, right. And they use hex back
Oh,
in
yeah.
the old days.
Yeah, so this is it right here. So we're loading all F's into the A, and then we put the A register into 6002, et cetera, et cetera. So that looks right. Does that look right, Casey? Did I get that right?
Perfect. PDP 2012 G.
You start recognizing the hex opcodes after a while. Right?
Yeah. The 12-bit machine, there was 8 registers, address mode, everything was 0 to 7 or to 5. Let's just go through some of my old pictures. I took a picture of the old PDPA front panel before it became recycled metal.
All right, let's see if this works. I think I got it on single clock here. Step through. Okay, we're coming to a reset. Oh, there's a reset. So 8,000. So store A, put all boxes, all bits high. We're going to write that out to, there we go. Yeah, so we wrote FF to 6002.
Look at the periods versus the backtick.
Oh, so what I did is I added, if it's printable hex, I just put the ASCII representation here. If it's not printable, I just put a dot. So sometimes I could, like when I was working on like the display, I was sending letters to it. I wanted to see what the letters were. So that's what this is, just an ASCII version of that.
Yeah, it just happens that some of those things translate to an
Yeah.
ASCII character. It's just noise.
Yeah. Well, sometimes I wanted to see the ASCII though. Like I'm saying hello world, I'll see, I want to see the H. So anyway, we load that guy, we load, what are we doing now? Right, oh, we write, so now we're writing 10 to 6,000.
Yep, it's there.
Oh, yay!
Let 'em LED, there you go.
Okay, so the next thing I did was, okay, now I know I can light this damn thing. like now I got to know which lights to light to make a number. So what I did was,
There's the PDP front panel.
Oh, yeah.
That was actually the later version of it. The earlier versions didn't use LEDs, they had incandescent bulbs. Yeah. And the bulbs, when they were on, were dim.
Yeah.
Did you break it again, Mike?
no, I did not yet.
Bulb burned out, it was off. There was nothing.
Okay, so the next version that we have here is this, instead of, or it's just, one of the things that the assembler gives you is definitions. So I can put in names of things, so I don't have to have to, like, if I see 6002 in my program, I don't know what that is. But I can actually put in like DDRB as the name for that. And then down here, I can use store DDRB. So it makes it a little more readable. And also it means that, like, if I have to change something, one place, it changes it all everywhere. So I can put my constants here basically. So this program does that. It adds some definitions that we can use in our program. And now instead of setting, I set my port all pins output mode as before, but now I'm going to clear the carry bit, and then I'm going to load binary, just a binary 1 into the A register, and then I'm going to write that out to the port, and then I'm going to rotate it, and then I'm going to go to the next one. So what this should do is you'd let one LED at a time, and I can see which pin is associated to which light. Now, if I could probably just do that with hardware, right? I could just move the wire around, but you know, why not? Let's do it with software. I'm a software guy, so that's what I did.
Yeah, that's what the ones. It's much more simple. You actually had less displays and you had a longer switch, which register going down.
Oh, makes sense.
There were these, actually, it was hallmarks.
Yep.
Instead of rockers. Yeah.
Paper tape?
Yeah. I still have my paper tapes. Maybe I can read them back.
Let's see if it works first.
Yeah, that was the front panel on one we had. And they're toggles. Yeah.
Got like a 120 volt.
Oh, it's doing it.
Yeah.
Doing it well.
Oh, yeah. It's raised up.
All right, so yeah, so it's going through each one. You know, lights one, we can light one, oh, it goes to 0 when the carrier gets back. So then it loops around. So what it's doing now is just basically shifting the accumulator and then writing it back out, shift, right, shift, right. So you can
How
see
come
it.
it doesn't write to the
Can you hold it up a little bit so other people can
Yeah.
see the LED a bit? See it dancing about?
Yeah. So yeah, there's actually a decimal point that I don't have a wire for
Oh, okay.
because I had only 8 pins and I need 1 for the ground.
Right.
And so I just cheated and I didn't need the decimal, so I didn't do
And
it.
just out of curiosity, what are those LEDs? the red ones?
Oh, these are just to see when I have
Oh,
the
when you're in the
switches.
switches. Okay.
Yeah. And this one's not connected to anything at the moment. Right?
Yeah.
So now we can light every one, and now we know which, if we go through and actually I already went through this exercise and see which data line is associated with which light. So we can just basically at my dining room table, I just map down like which light maps to which thing,
Oh, yeah.
and then I can get a bitmap, right?
Wait, you don't have a make file for that?
No, I don't have a make file for that. I did it with paper and pencil.
I keep
And
that around.
Yeah.
When I was in Sweden, I was snagging these A5 size grid as much as possible. I'm like, just in the store for $2, done.
so then I just put them in here. So this associated, so these are the bits I need to turn on 0, 1, 2, so on and so forth. And then when I got to 9, I realized, well, I can do A. I can make like a,
Oh, yeah.
A, I can make a little B, C, I go all the way to F, so I can get all 16 bits here. And like I said, the decimal point's not wired, so this bit is always off. So that's a waste of a bit, but maybe we can put like an LED or something in there, or maybe like connect that to a relay, turn on my coffee pot or something later. So then we do, yeah, it's the same stuff. Set up the port. So we outputs. In this case, now here's something new. Instead of loading the A register, I'm going to load the index register because we got to increment. So I load the index register, and then I load the A register with what's at the segments table offset by what the current value of X is, right? So it starts at 0, so it's going to be segments, the very first one offset by 0. So it's going to be this bitmap. Oh, so there's another interesting thing. So this segment starts at the top. 6502 doesn't care that you mix code and data. It's just all binary. It's
It's
jumping.
not Harvard.
Doesn't care.
Right.
So this actually is not opcodes. This is data, and we're gonna. So our reset vector is not going to start at 8,000 this time. It's going to start down here past this table. But we're going to load that byte, and then that should turn on the LEDs for that thing. And then I don't know what happens.
The thing that's now blowing my mind is not that we're able to do this. It's that I use this same chip to do word processing. On like near letter quality.
I don't know. It's amazingly simple, but it's fun for a hobbyist project because it's really simple enough you can understand it, but you can really do a lot. So then we store that, and then we bump X, and then I have to compare it because it's going to get to the end of the table. When it gets to the end of the table, then I just got to. If it's not at the end of the table, we just keep going to the next one. When it gets to the end of the table, we go back. Oh, we go back up to main loop and we reset the LDF. We reset X to 0 again. So B and E is branch not equal.
Yeah.
So we do a compare and then a branch. So that's how you do if statements in assembly. There's a branch if not equal.
Yes, thanks.
Can you hear me now? Yeah.
Oh shoot, I didn't have the thing in. Oh, now I screwed it up.
What's that smell?
The windows on the box, we can see how the bytes died.
All right. Okay, so what should this one do? Oh, this one should actually display numbers then as it goes up.
Have those ones with the crystal. It's like the lights in the office. Light it up.
Well, I know what the spell is.
If we get the little deeper levels.
Oh, here we go.
Oh, there you are.
There you go.
Go to, your whole set, right?
So we got this is where we need like webcam or something to show that.
I got one here.
Oh yeah, show the webcam. Let's start this over.
Let's see. This, you can, then I'll need to, well, unless you can plug the camera into your computer or.
No, I don't have more places.
Let me grab the BG or the port video. Off there for a moment. Plug it in over here. And. Okay, once that syncs up, get the cord out of the way. All right. There it is. Let
Oh,
me
okay, that was
change view.
0.
Hang on. Oh, come on.
It's backwards.
Foobar.
It's upside down.
Wait a minute. Let me, hang on, we'll take care of that.
It's mirrors.
There, that should change it.
It's mirror image.
Oh, it is, well, that's because I can do that. Hang on. Video, hang on a second. Let me change video to blur, virtual background, create video,
What are you trying to
video
do?
settings. I'm trying to reverse my video. There's
Well, you can just
That's
use
all
your
right, just
imagination.
Yeah.
No, because you've got mirror toggle to, there's the
Yeah.
checkbox.
Yeah, you have that one.
there we go.
There you go.
That explains why I was having a hard time.
usually makes sense, but it's hard when you're trying to position a camera.
Okay, so there's A. And this is B. Yeah. You turn the clock a little bit. There's C. I made the C a little tiny C. D.
You have two descenders?
Yeah.
F, and then we go back to 0. There you go. Okay, so now we can display. Now the next thing is, I'm gonna plug this back in. So now we want to be able to input something. So far, we've only done output. So we have to use the other port to do an input. So at this point, I'm going to add more definitions. So I have to add definitions for the A port, which is 6001, and the DDA for A, because that's going to be our input. And another thing is, for the input, I'm going to use the interrupt actually. So I hit the interrupt pins. It's going to interrupt. What we're going to do is we're going to set this up so the port A is read inputs. We set these to input whatever number we want, and then we hit the interrupt, and then the processor will go out and read whatever that port is set to when the interrupt is set. So it gives some time to get all the switches set up right. So there's a lot more setup to do. We have to set up the read handshake. Basically, we've got to set up these registers to say we're going to enable the interrupt. And there's a control signal A, A1, and A2. So A1 is on the input side, and A2 is on the output side. So what happens is the port says, "Oh, I've got the data," and then A2 sends information back to the peripheral, says, "We've read the data, so we're ready for the next byte." So there's the handshake there. So we set it up, and then we enable interrupts. So this loop's pretty much the same, but this is new, IRQ. So the first thing is, and also what's new is down here at the bottom. Before this is always 0. So now we're setting it to an address. So when the IRQ is enabled, the processor will stop what it's doing. It'll jump to this location. It'll automatically save its the registers for the program counter and the status. And then the first instruction here is to save the A register, the accumulator. And then we're going to read from port A and put it into the accumulator. We're going to chop off the top 4 bits because we only have 4 switches. And then we're going to store that at address 200, hex 200. And then we're going to go back to where we were. And I guess I'm going to skip to the next. The next one basically is the same thing, except in our main loop, we just loop and we just constantly read from that address that we're storing the data. So the idea is that we interrupt, we store it, and then when we jump back to our main loop, it should pick it up and then put it out on this display. You should have got a better socket. Oh, that's not right. Get in there. My pins are smashed. No.
Oh. Yeah.
Okay, Casey, did I get it in right? Okay, so now it's doing the setup. All right, so we got a 0. So what number? Let's start with number 7 is lucky number, right? So I'll go 0, 1, 1, 1, 1 to 7. Hit the interrupt. So that is the interrupt vector. I didn't wrote the 7 out. Maybe it's a little too fast to see that, but there it goes. Yeah, it wrote it to memory, but then it went back to the main loop and then take it up later. So that's nice and slow. Let's try another number. We'll try 8. Hit the interrupt. So this is pushing stuff onto the stack for the interrupt. This is reading the interrupt vector right here. So we're jumping to let me stop it. So yeah, right here. So these were pushing these values on the stack, which was 8032. That's where we were at. That's what we were executing at that time the interrupt came in. So when we're done with the interrupt, we got to go back to 8032. This is the status registers. It reads the interrupt routine is at 8003B. So we jump to 8003B to handle the interrupts. And then we push, this is pushing writing to the stack. This is page 1. Remember the stack's on page 1. So writing to the stack. We're saving our current A register. Then we read the 8 from the port 6001's read. Then we write it back out. Here's where we write it. And then we're going to go back. When we're done. We have to push stuff back out. And then we're going to jump back to where we left off at 8032. The 38. I'm sorry, 8038. So now we're back at 8038 in our main loop, and it should read the thing, and then it's going to update the LED. And now write it out to the LED. That's the bitmap for that. Write it out to the LED. So that's pretty good. And if I go, I can finally go to our fast clock since it's working now. And we can see if this thing actually works. So we can say, I'll start with 1, hit interrupt, and it didn't work. Oh, here we go. Interrupt. I hit the wrong button. 1, 2, 3, 4, 5. So I need to get a panel for this. This is 7, 8, 9, 10, 11, 12, 13, 14, 15.
Nice.
Yay! We're done. So yeah, that's it. And I bought one of these guys who have to use toggle switches. So I have to figure out how to do a scanner.
yeah.
Oh, I gotta do a
So 4x4,
matrix
and
scan.
It's got a scan.
Yep.
Do a scan.
He only has 4 switches now. We can hook up my DDR back to it.
That's true. Yeah.
I do have other. I have no set of switches. I was going to do. So I'm going to put the other switches on. I have a metal. I have a little box with cable closure to put the panels. So I got this guy, and I guess, and also I bought. This is Serial IO. I want to make an RS-232 interface.
Oh, yeah.
I got a console. Let me get a serial port.
Mhm.
So that's it's an RS-232C or?
This is actually a 6850.
Or 508.
Oh, yeah.
6850 chip.
You are.
mobile chip. So it's a serial IO. So this port right here, this is a parallel port. This is your. That'll be maybe next year, right?
Next vacation.
Next vacation. So thanks for your attention.
Very good.
So much.
Thank you.
I come here all the time.
Yeah, he's here all the time.
He's here all the time.
I just convinced Mike to give the talk. Sean and I convinced Mike to give the talk. And, well, Mike enjoys insults from the peanut galleries.
Yeah, very good.
What's that?
That's
You
the-
do the whole video card, one that he did on the.
Oh, that's my favorite one, actually.
That one
Yeah.
was really
So
awesome.
that's the thing. He's done a video card one.